Welcome back, everyone. Ready to dive deep into a new topic. This time, we're going to be untangling the fascinating world of electricity.
Yeah, it's something we use every single day, but probably don't think too much about.
Exactly. We're going right back to the fundamentals, even exploring a few things they might not have taught you in school.
Oh, absolutely. Like, did you know that the way we usually picture electricity flowing, it's actually the opposite of what's really happening at the atomic level?
Right. That whole electricity flows from positive to negative thing, total
It
misconception.
all boils down to these tiny particles called electrons.
Those are those negatively charged things whizzing around inside atoms, right?
You got it. And it turns out those electrons are the real movers and shakers when it comes to electrical current.
Huh, interesting. So it's not quite like water flowing downhill then.
Not exactly.
Mm.
You see, in a conductor, like a copper wire, those electrons are kind of loosely bound to their atoms. They can jump from one to the next, almost like they're playing a microscopic game of hot potato.
So instead of going from high potential to low potential, like gravity pulling something down,
They're actually attracted to areas with fewer electrons, those more positive regions. It's like they're always seeking out a less crowded party.
so the flow is actually from negative to positive. Mind blowing. I have to admit, I had that completely backwards.
It's one of those things that once you wrap your head around it, it totally changes how you think about electricity.
For sure. And, this probably seems like a minor detail, but understanding this whole electron flow thing is actually crucial for all sorts of technologies.
Absolutely. Everything from how we design circuits to the way batteries work, even how we generate and distribute power across entire cities,
Yeah.
it all relies on this fundamental principle.
It's like we're uncovering the secret language of electricity. But of course, if we've got all these electrons flowing around, we need a way to control them too, right?
Precisely. That's where insulators come in. They're like the gatekeepers of the electrical world.
Okay, so insulators are materials that don't conduct electricity well, like rubber or glass. But what makes them such good electron blockers? What's going on at the atomic level?
Well, remember those electrons we were talking about? They're organized in shells around the nucleus of an atom.
Right, like layers of an onion.
Exactly.
Hmm.
And the electrons in the outermost shell, those are called valence electrons. They're the ones that determine how an atom interacts with others, especially when it comes to sharing or accepting more electrons.
So are you saying that these valence electrons are the ones deciding whether to let those flowing electrons join their atom or not?
You got it. In an insulator, like rubber or glass, those valence electrons are very tightly bound to their atoms. They're not interested in sharing, so they resist the flow of electrons.
So conductors are like the life of the party, always ready to pass electrons along, while insulators are.
A little more reluctant to mingle, you could say.
Yeah.
They're the reason we can have safe electrical wiring and circuits, because they keep the electricity contained where we want it.
That makes so much more sense now. It's incredible how something as tiny as the arrangement of electrons within an atom can have such a huge impact on a material's properties.
It really highlights how everything in the universe is interconnected, even at the smallest scales. But speaking of scales, let's zoom out a bit and talk about how we actually measure and quantify this flow of electricity.
Okay, so we understand the basics of electron flow and the role of insulators, but to really dive deep, we need to learn how to speak the language of electricity, right?
Exactly. And that means getting familiar with terms like volts, amps, and ohms.
Right, those are the units we always hear about, but I'll admit I'm a little fuzzy on the details. So let's start with volts. What exactly is a volt?
Well, think of voltage as the driving force behind electrical current. It's the pressure that pushes those electrons through a circuit.
Okay, so it's like the oomph behind the flow.
Exactly. Imagine it like water pressure in a hose. The higher the pressure, the more forcefully the water comes out.
So voltage is like the electrical pressure, the force that gets those electrons moving. What about amps? How do they fit into the picture?
Amps, or amperes if you want to get technical, measure the amount of electron flow. Like how many electrons are actually passing through a point in the circuit every second.
So high voltage is like a powerful pump pushing the water,
Hmm.
and high amperage is like a raging river with a ton of water flowing through it.
Perfect analogy. And just like a river can be wide or narrow, electrical circuits can have different levels of resistance to that flow of electrons. And that's where ohms come in.
Ohms, right. It's like the friction that slows things down, right?
Exactly. Resistance, measured in ohms, is how much a material tries to stop the flow of electrical current.
So a material with high resistance is like trying to squeeze all that current through a tiny, tiny pipe.
Exactly. Even if you've got high voltage pushing it, high resistance means it's still going to be tough for those electrons to get through. Speaking of pushing, though, what about watts? That's the one we always see on light bulbs and appliances.
Yeah, watts. So that one's not just about the pressure or the flow itself, but how much work that electricity is actually doing.
Precisely. Watts measure the rate at which electrical energy is either being used or generated. It's like the power behind the electrical
Or
flow.
calculate wattage, we'd multiply voltage by amperage.
Exactly. So something with high wattage means a lot of electrical energy is being transferred, whether it's powering a super bright light or a heavy-duty motor.
This is really cool. We've got the pressure, volts, the flow, amps, the resistance, ohms, and the power. It's like we're cracking the code of electricity.
And here's the thing, these same principles apply, whether we're talking about a simple circuit you might build in a science fair or something as complex as the electrical systems on an airplane.
Oh, yeah. Speaking of airplanes, I was reading that static electricity can be a big issue for them.
It's true.
Yeah.
Might seem kind of harmless when it's just giving you a little shock on the ground, but up at high altitudes, static electricity is no joke.
What's the difference? Why is it worse for planes?
Well, think about it. As the plane's flying through the air, there's a lot of friction, right? That friction generates static charge that builds up on the plane's surface.
Oh, so like when you rub a balloon on your head,
Right.
but on a much, much larger scale.
Exactly. And all that built-up static charge can actually cause some serious problems. It can mess with the plane's sensitive electronic equipment, cause communication issues, and in extreme cases, could even be a fire hazard.
Wow. Definitely not something you want happening when you're thousands of feet in the air. So how do they stop that from happening?
Well, airplanes have these things called static wicks and bonding straps, which help to manage the static electricity.
Static wicks. Those sound interesting. What are they, like little lightning rods for planes?
You could say that. Static wicks are these small, pointy metal rods that stick out from the edges of the wings and tail. Their shape helps to dissipate that static charge into the atmosphere before it builds up too much.
Ah, so they're like escape routes for the excess electrons. And what about bonding straps? What do they do?
Bonding straps are there to make sure different parts of the plane all have good electrical connection. They create a low-resistance path for any built-up static charge to flow to a grounding point.
So it's like making sure everyone in a line is holding hands, so if one person gets a static shock, it doesn't zap everyone down the line?
That's a great way to put it. And those bonding straps need to be incredibly conductive. We're talking less than 0.003 ohms of resistance.
0.0003 ohms. Wow, that's incredibly conductive.
Yeah.
It really shows how even tiny electrical imbalances can have huge consequences in the wrong situation.
For sure. And speaking of powerful forces, it's time we talk about one that's invisible, but absolutely critical to how electricity works, magnetism.
Magnetism, right. We've talked about electrons and how they flow, how insulators keep things in check. But magnetism, that always feels a little more mysterious to me.
And it's definitely a fascinating force. A lot of people think of electricity and magnetism as totally separate things, but really they're two sides of the same coin.
Okay, interesting. So when I think of magnets, it's usually fridge magnets, or maybe those compasses you use in school. What's the bigger picture we're missing here?
It all comes down to these things called lines of magnetic flux. They flow from the north pole of a magnet to the south pole, kind of creating these invisible loops of magnetic influence.
So like an invisible force field extending out from the magnet.
Exactly. And these lines aren't random or chaotic. They actually have specific directions and strengths. That's why a compass needle always points north. It's aligning itself with Earth's magnetic field lines, like a tiny little signpost.
That's always been so cool, but I'll be honest, kind of confusing. But how does this connect back to electricity, the flow of electrons we've been talking about?
Well, here's where things get really mind-blowing. Just like when you have electrons flowing, creating an electrical current, those moving charges also generate a magnetic field around them.
Wait, so every time I flip on a light switch, I'm creating a mini magnetic field around the wires.
You got it. And it goes both ways, too. If you move a magnet near a wire, it can actually create or induce an electrical current in that wire.
So it's like a two-way street between electricity and magnetism. Electrons moving create a magnetic field, and then moving a magnetic field around a wire can also get those electrons flowing. No wonder they're inseparable.
Exactly. And the strength of these magnetic fields isn't always the same. It can vary depending on the material and something called permeability.
Permeability. Okay, now you're just using big words. What's that?
Don't worry, it's not as complicated as it sounds. Permeability basically describes how easily a material allows those magnetic field lines, a magnetic flux, to pass through it.
Okay, so some materials are like superhighways for magnetic fields, and others are more like roadblocks.
Perfect analogy. Iron, for example, has high permeability. Magnetic flux can zoom right through it, which is why we use iron in things like electromagnets. On the other hand, things like wood or plastic have low permeability. They're like do not enter signs for those magnetic field lines.
That makes sense. So we can use different materials and our knowledge of how electricity and magnetism interact to basically control and manipulate magnetic fields for all sorts of cool applications.
Absolutely. We're talking everything from the tiny magnets in your headphones to those massive generators that power entire cities. It all comes back to these fundamental forces of nature.
This deep dive has been incredible. It's amazing to think that these invisible forces are working all around us, constantly shaping our world. We've gone from electrons to insulators to the mysteries of magnetism, really digging into the fundamentals of how electricity shapes our lives.
And that's really just the tip of the iceberg.
Right.
There's still so much more to discover and explore in the worlds of electricity and magnetism. And who knows what other mind-blowing connections we'll find.
It's a never-ending journey of discovery, and we want you to be a part of it. We hope you've enjoyed this electrifying deep dive. Until next time, keep those questions coming, keep those minds curious, and we'll see you in the next episode.